All right, welcome. So in this video, I want to continue our discussion of recursive algorithms. And like I've done before, I want to continue talking about an algorithm that we've probably seen before. We might not have seen it recursively before, but of course we've seen it before because we talked about it earlier in this sequence of videos, the minimum algorithm. But now I want to try and solve it recursively, again for the purpose of continuing our discussion of recursion, introducing our discussion of recursive analysis, and not getting bogged down in the details of the algorithm itself, since the minimum algorithm is one that we're already familiar with. Let's just quickly revisit the definition of the minimum problem. Given a sequence of integers, we'll stick with integers for the moment. We want to find the element of that sequence that is less than or equal to all of the other elements of that sequence. Okay, so we already wrote an algorithm for this with a loop, but now what we want to do is try and come up with a recursive algorithm to do this. Now, to do this, there's actually more than one strategy we can do. And in fact, there's actually a great deal of interesting strategies we could tackle. But I really just want to start with the easiest one, or the one that comes to mind first, which is the idea of maybe splitting off one of the elements. Doesn't really matter which one for the moment. Splitting off one of the elements and then saying to ourselves, well, we could recursively find the minimum of the remaining elements, the remaining n-1 elements. That's our smaller portion that we'll recursively do. And when we're done, that will spit back some number, the minimum. And we can compare that minimum to the number that we've split off, the extra one that we took off, and determine which one is smaller. Whichever one is smaller is the true minimum, of course. So this idea, because I haven't been very clear about which item I'm going to split off, gives us technically n different algorithms we could come out with. Do we split off the first element, the second element, the last element? And each one of those is a correct algorithm. But some obviously are a little bit more intuitive than others. Picking the middle element doesn't seem as intuitive. Let's take a look at what I've done here. Now, I think picking one of the end elements is the most intuitive. Picking 1 or n is the most intuitive. I've chosen to pick the last element and break it off here. We'll see that here in a second. Because it makes it very clear that the size of the group that I'm calling here is of size n-1. So I've chosen that on purpose just so I could write 1 to n-1 here instead of 2 to n if I split off the first one. Both of them would be of the same size, but this just makes it very explicitly clear. So that's just to justify why I've chosen this minimum algorithm over some of the alternatives that are honestly equally valid or equally worth considering. And you know, maybe like me, you might think I actually like the algorithm where I split off the first one better. But because, remember, sometimes we design our algorithms for a purpose. I designed this one, well, for a handful of purposes, but in particular to analyze it, but then also as a teaching tool. And I felt that, hey, having it go 1 to n-1 just makes it clearer. It doesn't have as much, confusing obscurity in it. And so I opted for this. So let's see how we go with this. Now let's take a look at the algorithm in a little more detail, since I just sort of jumped to this one detail. What do we do? Well, okay, the minimum algorithm starts out probably the way we would expect. We take our input in. Nothing surprising there. But then what we're going to do is we're going to have to think recursively. So remember, if you've dealt with recursion before, the first step is how we terminate, which is when do we stop? Well, in this example, I guess I didn't really say in my example idea here what I was doing. I'm going to split one off and find the minimum of the remaining elements. Well, that works until what? Well, until we get down to a small enough group that we can't split any off anymore. And usually that means, well, I guess we could have decided to terminate at one of maybe 3 different locations. We could have actually terminated when we just got to 2 elements. Because once we get down to 2 elements, we could just do a simple if and return the smaller of the two. We could do that. But as I've done, at least in this code, I've decided to go down to one element. Because if we're trying to find the minimum of one element, it's just that element. We don't have any work to do. We just return that element back. So that's what my first bit here is. If n is 1, there's only one element, just return it, and we're done. So hopefully that's all we need, and in a second we might verify that. But I said we could have three possible places where we could try to terminate. The other possible place I would always consider, although in this case I don't think it will work, is we could also try n equals 0. Now whenever n equals 0 works, I usually like it. I like to use it. And the reason for that is because whenever n equals 0 works, usually the answer is very, very simple. It's like 0, or it's null, or it's something so simple that you don't have to put a lot of thought into figuring it out. This case probably didn't have to put a lot of thought into it either, but maybe a little bit of thought, maybe like a little sliver of thought to figuring out the answer here. But in this case, actually, n equals 0 doesn't really make sense. And I think I talked about this in the earlier video. What do we really mean when we ask, well, give me the minimum of this empty set, of this set of 0 elements? So I want the minimum element out of it. There are no elements in there. And so we find that question, or that input, to be not well formed. Okay. And so if we really wanted to build this into our input statement up above here, we could say where n is greater than or equal to 1, and stress that it can't work for 0. So in this case, I feel like I've probably picked the best terminating case that I could come up with, at least, for this design strategy, recursive in its strategy. So now that we've gone through the terminating case, we enter the else condition. I've got some indent here. Just in our last video, we had a very simple example where all this happened on one line. Well, now I've got multiple lines, so I've got at least some scope identifying with my indentation here. And let's see what happens. Well, in this bit here, I actually have a lot of different work going on. Remember, when we get to the analysis, we're going to split this into the recursive work. So this little bit on this line here, at least, I'm going to highlight as a recursive call. We can see it's recursive and getting smaller, so hopefully we're confident that this will terminate, this will eventually get down to size 1. And what do? Well, in this case, we record whatever is returned by this recursive call in this variable m. So that's the minimum so far, if you like, or the minimum of this recursive subcall. And then the element that we didn't include in that set was an. So now I will check an versus m. If it's the smaller one, I'll return it. Else I return m because it's the minimum. Again, hopefully we put this through our internal intuitive compilers, and we sort of say, yeah, that makes sense. This sort of is correct. I'm not going to actually try and prove this correct here. In fact, there are other techniques that we could use to prove this correct, but we've kind of already proven this strategy correct with our loop. Now what we're just trying to do is see, is this a more efficient way of doing it or a less efficient way, or is it the same degree of efficiency as our looping structure? So that's really where I want to go next. So instead of sort of focusing on the correctness, let's focus on the analysis. So as I mentioned, let's now take a look at how many operations are carried out by this recursive algorithm. Now in the last video, I went over in some detail what we're going to do. We're going to split this into two cases. At least at first, we're going to split this into the terminating case and the recursive case. And then when we get to the recursive case, we're going to split that into recursive work and other work, non-recursive work. Let's start with the easy case, the terminating case, non-recursive case. This will be when n equals 1. When n equals 1, we'll have one method call, one comparison, one return. It looks like similar as last time. We're going to do 3 operations. Now this is a more complicated recursive algorithm than our Fibonacci series, so we're going to want to be careful in calculating how many operations. Now remember, we're going to split it into 2. Luckily, we are a little bit easier on the recursive operations side. We only have one recursive call in our recursive case, and that's this one here. and it is of size n minus 1. So that's going to be pretty easy. We're going to have a t of n minus 1 in there, plus other stuff. What other stuff do we do? Well, I'm going to be careful. So we did one method call to come in. I'm counting as I go. 1, 2 to get this comparison, but not this one because we're skipping. We're going into the else. So we're at 2 here into the else. Now, I'm not going to count this recursive call because I already got that on the side, but I'm counting the non-recursive work. So it looks like, again, I was at 1, 2, 3, 4, 5. Now, do I count this return or this return? Well, whichever branch I go down, I get one more, so it looks like 6. So let's go through that again. 1 for the method call, 2 for this check, but we don't go here, we go into the else. 3 for the assignment, 4 for the minus 1, 5 for this check, and then whichever branch we go down is 6. We do the 6 for the return. So I end up counting out 6 operations. And so this gives us this recurrence relation. Let's make sure we got this right. We counted 3 in the case when n equals 1. That was our terminating case. And then we said we had one recursive call of size n minus 1. So there's sort of an invisible 1 out front here saying one call of size n minus 1, plus the 6 other operations we counted that were not recursive. So that gives us this. Now, let's think back to the Fibonacci example in the last video. In that one, we had t of n minus 1 plus t of n minus 2 plus 6 or something like that. I don't remember what the constant was, but some other constant there. In which case, the only real difference here is we've changed this so that we no longer have this t of n minus 2 term. And that simplifies things a little bit, which is going to make our next step, our next bit of analysis, easier. So let's see if we can figure out where we can go from here now. Okay, so now what we want to do is we want to kind of figure out a version of t of n that doesn't have all this recursive bit in it. Okay, so let's focus back on what we did when we were looking at iterative analysis with loops. We ended up getting to a point where we could express the cost of the loop as a summation. And then we said, well, we don't really want the summation in there. We want something that looks just like an f of n. So we went through some of the steps that we could use to eliminate the summation in our math and just give us a nice closed form or simplified expression just in terms of n, a nice simple function. Well, that's the same thing we kind of want to do here, is we've got a recurrence relation here, a t of n now, and this recursive bit makes it sort of hard for us to see, hey, is this big O of n? Is this big O of n squared? What is the asymptotic running time of this? It's hard to see in this structure, just like it would be with a summation. So we now want to go through steps, tools to eliminate it. Now, to do this, I'm not going to jump right into the techniques that we might use. Instead, what I want to do is explore a little bit. So we can see that the first value that we encounter is just t of 1, of course, which by definition is just 3. And what we're going to look for here is a pattern as we go. And I'm just going to say, most of the time our brains are pretty good at picking up patterns, so I'm going to say let's just investigate a couple more. So let's do t of 2. Now what we'll notice if t of 2 fits in this case of n greater than 1, right? So when we have t of 2, we need to use the recursive definition that would tell us that t of 2 is actually t of 2 minus 1, or t of 1 plus 6. So t of 1 is 3, so t of 1 plus 6 must be 9. So that's got the step here. So t of 2, using the recursive definition, is t of 1 plus 6, 3 plus 6 is 9. Okay, well then what would t of 3 be? Well, t of 3 then would be t of 2 plus 6. So t of 3 is t of 2 plus 6, which, well, just expanding out my math here a little bit, is 15 now, or 9 plus 6 is 15. Now here, the reason I've written it this way is it's showing me that as I unwind here, I keep adding 6 on. The reason I did this is I'm going to be able to pick out a pattern here in a second. Let's do one more. Let's see what t of 4 is equal to. Well, t of 4, of course, will be t of 3 plus 6. So we get t of 3 plus 6, which is 3 plus 6 plus 6 plus 6. We got another 6 on there now. 21. So the purpose of doing what I'm doing right now is to try and see a pattern. Okay. And so if you think you've seen a pattern already, well, you tell me what you think the next row would be. Okay. I'm guessing we're probably going to add 6 on there again, right? So what, 27? Okay, and then 33. And if we can see a pattern like this and we think we can see that pattern and we can run with it, then why not translate t of n so that we don't have to write it in this way? We don't have to write it recursively like this. We can write it just more naturally as a mathematical function. And so I've got a little bit of a guess here. Now, well, there's spoilers here a little bit, but it says we're adding 6 every time, but you notice we didn't add 6 the first time. Okay, or maybe we did, but it didn't show up in our math here. We just had the 3 by itself, then we had 3 plus 6, then 3 plus 6 plus 6, and so on. The number of 6's on the end is sort of like the n we've got here, but as we can see in the formula that I've come down here, it's not exactly right. Here we have t of 4, but we only have 1, 2, 3 6's. So the way I wrote it, at least the first version I wrote here, was we had 3, yes, 3 shows up on all of them, plus 6 times however many times we need it, depending on our input n. In this case, it's n minus 1. Let's just make sure that, double check. If we plugged in n equals 1, we get 3 plus, this becomes 0. So we just get 3. If we plug in 2, we get 1 here, we get 9. So we can see that this is indeed correct. And then all I've really done is simplified a little bit here to say we could have written this as 6n minus 3 or 6n plus a minus 3, which basically is saying, hey, see this 3 that we've got in here? It's really a 6, but there's a minus 3 on there that we didn't mention. So that's just another way to write the same pattern. Of course, I've written this one because this is one with that sort of isolated like terms and written it in order of degree, meaning that we put the dominant term first, in this case, degree 1. Ending up with a 6n minus 3 as our number of operations carried out by this recursive algorithm. Now, what I want to complete this video with is sort of a proof that this is correct. What I just did on the previous slide, if I did it careful enough, and I didn't make any mistakes, so I actually did it carefully enough, for many people might constitute a proof. But we have a more rigorous tool in our toolkit, which is induction, which we can use to actually carry out this proof. So I do want to do one proof here to make sure that this is true using induction. And again, this is a great example to show us another application of induction, which gets applied all over the place in mathematics, and then also gives us the opportunity to, well, see how we can use it in this instance, that is applying it to recursive analysis, recurrence relations, and recursive algorithms. So let's do that here. So I claimed, at least on the previous slide, that t of n here is equal to 6n minus 3. Can we prove that that is true? We kind of verified it a little bit already in our head. But we're going to do this by induction on n. And as we do with induction, we're going to start with a base case. Now, one of the reasons why we use induction when we're working with recurrence relations and recursive algorithms is because induction is, the structure of induction rather, is itself recursive, and so it maps very perfectly into the structure of recursive algorithms. So proving the runtime of these recurrence relations is sort of a natural application of induction, because why? Well, we have our terminating case sort of right here. So our base case and our terminating case match up a little bit. If I want to prove my base case, why don't I prove n equals 1? And let's see what we got to do here. So that's what I'm going to do. Base case I'm going to prove is n equals 1. And what is it that I need to prove? Well, imagine plugging 1 into our equation here. That would say that t of 1 is equal to 6 times 1 is 6 minus 3 is 3. T of 1 is equal to 3 is what we need to prove for our base case. Well, what is t of 1? It's 3. Okay, we're done. So actually, this line here sometimes when we write these lines, it looks very simplistic because really what we're doing, we're not so much as proving something here. I mean, we are kind of. We're more sort of verifying. At least that's how I approach the base case. Is I'm saying, I just check to see what is it I'm supposed to prove here. And then usually in the process of checking to see what it is you're supposed to prove, we get to something as simple as saying, oh, I'm supposed to prove that 3 is equal to 3? Well, okay, I'm going to take that as a given. I'm going to take that as an axiom. I'm going to say that most of my readers already know that 3 is equal to 3, so I'm done. So really what I've done here is on the right-hand side here, you can see I've written this 6 times 1 minus 3. And then on the left-hand side, I had plugged in my t of n, and I just sort of showed in the middle, they're the same. T of 1 is 3. Doing some math on this is 3, so they're the same. Now, often when I do this, I think I've mentioned this before, in my base case, once I've verified it's correct, I sometimes put a little check mark there and just be like, I'm done. Or if there's sometimes a condition that I need to remember, like this only works when 3 is equal to 3, well, 3 is always equal to 3, but you know, if this only works if a is greater than 5, I might put a little note to myself, remember a has to be bigger than 5, or else this doesn't work. This case works no matter what. So this is just a check. Yep, correct. Okay, so now let's get to our inductive hypothesis. Now, we've used our induction in a couple ways so far. And I'm trying to work us up to a type of induction called strong induction. We're still going to be using what's known as weak induction. But so far when we've been doing weak induction, we've been assuming what we've been trying to prove, basically for n, for our current value of n, and then we've tried to prove that if that was true for n, it would still be true for n plus 1. And that is, of course, a valid application of induction. That's what we've been doing. But I'm going to shift our notation a little bit now. Instead of talking about n and n plus 1, I'm going to talk about n minus 1 and n. So I'm going to say instead of assuming this is true, that t of n is equal to 6n minus 3, I'm going to assume it was true for the last instance, that t of n minus 1, and then I'm going to be careful to plug my n minus 1 in for n here, that t of n minus 1 is equal to 6n minus 1 minus 3. Then what I'm going to do in my inductive step, or in my inductive case, is I'm going to talk about n itself, not n plus 1 like we had done in the past. Now, you can do this exact same proof as we had done in the past with n and n plus 1. I'm just showing us here how we can do this again in terms of n minus 1 and n, because, well, in a couple videos from now, I'm going to want to do something again called strong induction, where we're going to have to make an assumption about a whole bunch of previous examples, not just the last one, in this case n minus 1. So we've assumed that this is true for n minus 1. That's my inductive hypothesis. Let's go ahead and apply it in my inductive case. So inductive case, my n will be greater than 1 because we already handled n equals 1 up above. So let's start. Now, when I do these inductions, especially on recurrence relations, the steps that you need to follow are usually straightforward, meaning that every time you get to this point, you follow them in the same order. The only cleverness comes in if you can remember, hey, what steps of algebra do I need to use? What maybe steps of approximation do I need to use if you're using approximations? In this case, we're using equality, so that won't come into this particular example. But we do have to do some algebra, so we want to make sure we do that right. But the first step, we always just write down what we know, which is, as we've seen in a lot of the proofs we've done so far, the first step is usually apply the definition. So what is t of n? It's, in this case, since n is greater than 1, we know it is t of n minus 1 plus 6. So that's all I've copied down here. T of n, by definition, is t of n minus 1 plus 6. Often, when I actually write these proofs, especially when I do it for students, I'll write a little comment here, sort of like I'm writing it in C or something, put a couple slashes, and I'll say, by definition, right after it. And that's a great little note to your reader saying, hey, where'd you get this? Oh, from definition. If they weren't really paying attention very closely, they could look back up above and say, oh yeah, that is the definition. Then we hit the next step. If we've applied the definition in the first step, the next step, usually almost exclusively, is apply the inductive hypothesis. The purpose of the inductive hypothesis is to give us something to replace the recursive term here with a non-recursive term like we've got here. And look, we've got that exact recursive term here, t of n minus 1. So since we've assumed that t of n minus 1 is equal to 6n minus 1 minus 3, we can do a replacement now. So I'm going to do a swap. Swap out that t of n minus 1 for what we said it was equal to, 6n minus 1 minus 3. Now is when the algebra comes in. Well, again, as I mentioned, we want to make sure we do our algebra correctly, but this is easy algebra. Distribute the 6 in, we're going to get 6n minus 6. And well, I left them all out there, but let's cancel our 6's, and we got our 6n minus 3. That's what we were aiming for, right? T of n, we showed, was equal to 6n minus 3. So a little bit of algebra, but let's go back and remember. First step, apply the definition. Second step, replace that recursive term using your inductive hypothesis. Swap it out, and then usually it's a little bit of algebra that's left to manipulate what you have to get it to the goal line, which is what you're aiming for here, what we had written above in our theorem. We're not quite done because usually we like to finish off with a little statement saying, hey, we did what we said we were going to do. By induction, we have shown that t of n has the bound that we said it had, which in this case is 6n minus 3. Okay, so let's just do a quick little bird's eye view refresh of what we've done here. We've taken our recursive code for the minimum algorithm, created this recurrence relation that expresses how many operations it was, and then we asked ourselves, well, hey, well, what is a simplified version of that? Just like we would do with the summations, we did that here with our recurrence relation. And then, using a little bit of math, a little bit of tools, we found that we could prove here with induction that this was indeed equal to this more simplified version, 6n minus 3. And using the techniques in our earlier videos, we could say, well, this is theta of n, big theta of n, which maybe on the bird's eye view, we would say, well, that's no better or worse than our original algorithm for this that was iterative. Now, it's been a while since I made those videos, but I think if we wanted to go back and compare that algorithm, the iterative one with the loop, to this one, the recursive one, we would have to compare these two functions very fine-tuned. This 6n minus 3 versus the other one, and if I can remember properly, and I'm guessing really here, I think it was 4n plus 1. Something like that, I don't know. The important thing here, not so much the plus or the plus 1 or the minus 3 here, the more important thing here is what number came out in front of this n. 4n or 6n, if you have to pick between them, at first we say they're both n and we might say just as good as one another. But then if we start nitpicking and we look at those constants out front, we might say, hey, 4n's better than 6n. So I prefer that one. Okay. But again, as I mentioned, asymptotically, they're the same. Now, why here did we get this? I think, at least this is true in a lot of systems, not always, because systems can be optimized against this, but a lot of times recursion has a higher, what we'll call overhead than looping, okay? A higher overhead. So what's the overhead in looping? The overhead in looping is like incrementing I, checking it against your terminating condition and so on. That's what we call overhead. The work you got to do, no matter what's in your loop, you got to do that for every loop. In recursion, the overhead is the method call, as I mentioned a little earlier in this video, putting things on the stack, popping things off the stack, in this case the memory stack, variables that you might be working with. And so that overhead typically, most of the time, turns out to be greater than the overhead of loops. Meaning, if you have a choice, should I do this with a loop? Should I do this with recursion? Most of the time, I'm going to say 90% of the time, you're going to say, I should do that with a loop. But what makes that choice is what language you're working with most often. A lot of languages are not very well optimized for recursion, but they are very well optimized for loops. If you're in that type of language, then you should probably use looping as much as possible. I think a lot of the C type languages are like that. C, C++, C Sharp, Java, and so on. A lot of them are more optimized towards, what did I say, looping structures than recursive structures. Now, that's not saying that they don't have any optimization for recursion, just that other languages are optimized in the other direction, towards recursion. Some are so optimized towards recursion, they don't even have loops. The only way to do things is recursively, in which case you would have to do your minimum in this way, okay? But as I mentioned, then some languages are in the middle. I think really those C-type languages in Java are a little bit more in the middle. They've got optimization for loops and optimization for recursion, especially if you do what's called tail recursion, which is where your recursive call is the last thing you do in your recursive function. Now that's a special kind because it can be optimized better, and it might reduce that overhead a little bit. Okay. In fact, tail recursions can be very easily optimized as just loops anyways, and often that's how the compiler will do it. The purpose of discussing this sort of difference between recursive code and looping structures that can maybe carry out the exact same algorithm, a lot of the time, unless we're in a recursive structure where recursion has already been optimized, we want to avoid it. Now, with that said, as a programmer, I use recursion all the time because, well, our machines are pretty fast, and the difference between the 6 and that 4 that I mentioned is not a difference that I usually care about. And there's often, for a lot of code, writing it recursively might mean writing 3 or 4 lines, whereas writing it iteratively means writing 30 or 40 lines. And hey, my fingers only have so many clicks in them, so I only want to click so many clacks. So a lot of time I'll write code recursively instead of iteratively if it's just easier for me to conceptualize or easier for me to code. Okay, I think that's all I wanted for this video. Stay tuned for the next one where I'll do some more recursive analysis. We'll do this again on another recursive algorithm. So thanks a lot for watching, and we'll see you in that next video.